All right, so we have now, okay, so we will conclude this conference, which with Xenia Ossa from Oxford University. She'll be speaking about geometry and deformation theory of heterotic systems.
Sorry, where? Trying to find the point.
Oh, the pointer. Zero. Right, zero. Okay.
Okay, well.
Can you click? Here's the left and the right. And the center is for the laser to shoot people. Yeah.
Mention to the ice.
Okay, let me compose myself. Okay. Okay, so well, thank you so much for the invitation. I mean, this has been a very nice conference. So along the course, yes, the days have gone by, I've been taking things out of the talk because there has been such a lot of discussion about the geometry and deformation theory of heterotic systems, in particular this Strominger whole system. So, but I still would like to give an overview, but in reality, I will focus on the G2 case. So, because so much has been said already about the Strominger whole system, right? So, but I still try to give a sense of unity for the three of them, for the three of them, meaning the Strominger whole, the G2 system, and the spin 7. So this is meant to give an overview. So this is has been a nice journey with my collaborators and for many years now. And this doesn't mean that we are the only ones, as you have said, as you have seen in this conference, right? That have discussed the heterotic system. But of course, I will present here my own perspective on this. I mean, as a physicist, in fact, right? So I will the references in red are the ones I will discuss more today. Okay, so let's start with the general context. Right? What's the general context? I mean, of this work. I mean, we are string theories. So I'm interested in the effective field theory derived from minimally. I am particularly interested in the minimally supersymmetric case compactifications of heterotic string theories and the conformal field theories that come out of this. So and of course, what are the mathematical structures that we encounter? And of course, we are familiar with the very beautiful structures in mathematics and physics that arise from string theories and corresponding CFTs, the many years that have been going on. So, so heterotic string theories, I mean, they are 10-dimensional supersymmetric gauge theories. They come classically with a vector bundle V with connection A, which has a structure group containing A plus A. And this is different from the type 2 case and in theory, where you have to work hard to get a Yang-Mills theory, right? In type 2, you need to add brains and stack brains and things. If you don't do that, you end up with a theory that has only one gauge theory. And as Magdalena mentioned earlier, in M theory, to get some interesting physics, you need to compactify on something that has singularities or other complications, right? So this is why I like it at this time, but of course this makes it harder in some sense. So it has been in some sense neglected because of the bundle, right, that appears in 10 dimensions. The physics will. So to study the effective field theories of the heterotic string compactifications, which give minimally supersymmetric gauge theory in space-time, we make an ansatz for the 10-dimensional metric, right? We say that our 10-dimensional space is a product or a work product of a d-dimensional space-time, which is maximally symmetric, and a little d dimensional internal space y. So that's an ansatz. One can relax that ansatz, and in the case of the heterotic, I mean, there is work by Grant, Lorman, and Papadopoulos in which they relax these, and they only require supersymmetry, preservation of at least one supersymmetry, and they get more general geometries than this. So we'll be interested to study those in the future, but perhaps we should stick with this time. So you have seen this in a few talks now, but let me say it again. So we have the following mathematical objects of this series, right? We have a Riemannian metric for the orbital manifold. We have a scalar field, which is the dilaton. We have gauge fields, right, for the gauge group containing A cross E8. So B is a vector bundle on Y with connection A with structure group G containing A cross E8, as I said, here. And then we have this pesky freeform, right, the flux, right, that mixes all the degrees of freedom in your theory, right? And this flux is defined by this equation. So these are the Chern-Simons forms for the connection A. And we also have a connection theta on the tangent bundle of Y. And we have here an object that is called the B field. And it's not, I mean, the three form is a well-defined free form, right? But the B field is not, right? It's not gauge invariant. I mean, compensates, I mean, the transformation properties compensate those of the Chern-Simons. So again, this is different from type 2B theories in which you don't have these extra beats there, and the B field is basically well defined. So what we have, and again, as you have seen in the talk by Matteo and Maddalena in particular, right, and well, Philip too, so that we have, what we have is a quadruple, right, a manifold and a bundle with connection, a tangent bundle with connection, and a form, and a free form. So when we say that we want, so we start with this space, if you like, the total space of the bundle, of these bundles on the manifold and this H, and then we ask what supersymmetry does, right? So mathematically, supersymmetry constrains this geometry, the geometry of this object, and together with the requirement that we also satisfy the equations of motion, we obtain what we call the heterotic system, right? So I have added to this structure this eta, meaning that when you require supersymmetry, you are demanding that you have spinors on your manifold, and these spinors will be covariantly constant with respect to some connection with torsions. So basically, a structure group of your manifold Y will be used. So you have a G system. You know? And this eta just here just represents the fact that you have a manifold with this extra structure, with an extra G structure. So in physics, our goal is to construct a quantum effective field theory, right? Which is largely determined by the geometry and quantum moduli of this compactification. So we're very interested in that. So, so we want to find at least as a spectrum and effective four-dimensional Lagrangian, eventually correlation functions and solid dualities and so on. So, okay. So again, this is a repetition of previous talks, right? So this is a heterotic system. Now I'm posing supersymmetry. So now this manifold, we have an integrable G structure, right? In the case in which your spacetime is four-dimensional, you get the Strominger system, right? That has which is a G structure with particular some other constraints. In the vector bundle and the tangent bundle, we'll have instanton connections. I will define them later in the example we'll talk about. So, but we have seen that in the Strominger whole system, means instanton means this, and then we have the anomaly, right? But what supersymmetry requires is that the flux equals a three form T. right, which is the total antisymmetric torsion of the connection of the G connection, right, or a connection compatible with the G, your G structure, right? So your forms will be combined with constant with respect to this connection. But notice this word integrable here, right? What we will mean in this talk by integrability, at least, is that we have a connection that admits a total antisymmetric torsion, right? That's not always the case. As confusing, and I agree with the comments before. I mean, these are confusing. But if somebody can come up with a better name, that'll be good. But that's what we will leave with that. So in the strong meter-Hall system, right, this is the Bismuth connection, which is the unique metric connection compatible with the SN3 structure, which admits a total antisymmetric torsion. So today I'll focus on the case of the 7-dimensional case, right, where one has a G2 structure. And one of the reasons is because, as I just said before, there has been a lot of discussion about the strong meter-Hall system. And moreover, we can well, whatever I say here will be useful, I mean, for the strong meter-Hall system, because you can deduce it from the G2 case. There is also the spin 7 case, is also very interesting. I mean, this basically followed on my lab. It is almost identical in some sense to the G2 case, but I won't talk about it today. Let me just say that it's very, very similar in flavor. And so another reason I want to focus on this is because much less is known. So there is an exploration now, I mean, about three-dimensional theories with n equals to 1 supersymmetry, and much less is known about this. Right, so in the heterotic case, the three-dimensional space will be given the answers that we have, will be ADS3 or three-dimensional Minkowski space, and compare this, for example, with what happens to 4 dimension with 1 supersymmetry, right, which is like 3 dimensions with 2 supersymmetries, said in a superficial way. So compactifications to 4 dimensions with n equals to 1 supersymmetry gives strong constraints on the geometry and on the moduli space. So as Philip described earlier, I mean, the moduli space must be complex and Kähler, and he gave you a metric, a Kähler metric for this moduli. But we have no such theorems for 3 dimensions. Particular holomorphy plays a very important role here, and we don't have anything like that. So we are trying to discover what it is that we can say these cases. So
what will be the expected geometry of the scalar manifold in 3 dimensions?
The space-time manifold?
No, the expected geometry of the scalar manifold coming from n equals 1 supersymmetry in 3 dimensions. Is it constrained?
Of the scale of the moduli space?
The moduli space.
What would be I don't know.
Yeah.
So that's what we are trying to.
No, I mean just from purely 3-dimensional field theoretic supersymmetric arguments.
No, I don't know.
There is a real superdimension.
Yeah.
There is a real calendar.
I see.
So I'll show you what Eric is saying. Is something that I will show you at the end.
Okay.
There is some space in superpotential, and one can say something from that.
But then other
Sure.
Yeah.
But I thought there would be other constraints.
No, I will show you at the end. Yeah. So this. Yeah. So this is. Yeah. So anyway, so this much to learn in this case. So the key ideas in this talk. So I said I have reduced it to. I am tired. So I will be quite concise today, right? So as I said, I'm taking things out of the talk because so perhaps I should just focus on this, right? So
can I comment on this?
oh, what, sorry?
When you say equivalent, you're showing something on the right.
Let me say it and then then you can comment. Yes. Okay. So you have this has been discussed in talks, right? So the conditions for this object to admit a heterotic structure have been stated, right? But what I want to tell you is that this is equivalent, apart from Eric's comment, very equivalent to the existence of a differential that encoded operator, that equals to 0, that acts on forms with values on a bundle on Y. And the bundle topologically is this. So this is something I will tell you about today. And then I will argue that the small deformations of the heterotic system correspond to classes in this object, the first cohomology of this operator. Okay. So that's basically the content of the talk. Eric, you wanted to say something?
Yeah. I'm just gonna, if someone's interested about that, then they can ask me later. But yeah,
So you won't comment? No?
You have to enlarge the system slightly. What do you mean by the heterotic system?
Yes, it is. It indeed. Yes. So yes. So I was trying to avoid some details, but Eric is right. I mean, this is a slightly enlarged heterotic system, in the sense that we are not. For example, we are not setting tau 1 equals to d the dilator. For example, this is one example.
It has to be close to your properties.
Sorry?
But it's still a close.
It's still the check close, but it's not. So there is it's slightly enlarged, but if we find it, we still. I mean, you can find the physical modular expression from that. So it's okay.
Sorry, this discussion applies only to the G2 system, or
I can make the same statement for the spin 7, for example.
Okay.
But of course, in that case, you won't have a 3 form. So in the G2 case, what you have is a 3 form, as discussed before. In the spin 7 case, you have a self-dual 4 form, right? And but everything else follows. Okay, so this is the outline. I'll repeat what it said, but with a twist, right? I will rephrase what I mean by an instanton, for example, like this. And then I will tell you about this space of small deformations of the heterotic G2 system. I will start with just the deformations, flows, if you like, of the G2 structure, and then include the bundles, and then include the Bianchi identity. And then I'll try to have some 5 minutes to discuss some kind of problems. Okay. So this again has been said many times during this conference, right? So supersymmetry requires that Y has an integral G2 structure, right? So a manifold a manifold with a G2 structure is a 7-dimensional manifold Y, which admits a smooth positive 3-form phi. And in fact, any 7-dimensional manifold, which is spin and orientable, admits a G2 structure. The 3-form phi determines a Riemannian metric, and with that you can form the dual of the 3-form and get the 4-form psi. So the exterior derivative, I mean, as you saw in Mateo's and Magdalena's talk, the exterior derivative of phi and psi can be decomposed into G2 irreducible into representations in this manner, where tau I are I forms, are forms of degree I, which is called the torsion classes, in fact it's the intrinsic torsion, and are uniquely of a connection, right? And are of a G2 compatible connection, and are uniquely determined by the G2 structure phi on Y. So it's by this unique decomposition, right? So these are the irreducible representations here. So an integrable G2 structure satisfies tau 2 equals to 0. So this piece here is not there. So is a very neat way of rewriting these structure equations when tau 2 is 0, which is by using insertion operators. And this is the torsion of the intrinsic torsion of this. Sorry, let me say something else. So when tau 2 is 0, this is the condition that you need for your G2 compatible connection to admit a total antisymmetric torsion, right? So it's necessary for us to have it there. And the total antisymmetric torsion, there is a unique such thing metric, which is this given by this formula. And it's a very neat way of writing the structural equations in terms of insertion operators. Right. If the torsion is 0, right, this means that, that all the torsion classes are 0. And in this case, you have T2 holonomy, right? And as I just said, T is the torsion of the unique connection, nabla, compatible with this integral G2 structure, right, which is totally antisymmetric. So let me make an observation. This tau 0 here, this is scalar, it's a function, right? When it is 0, then you have Minkowski space, this space is Minkowski. And when it's not 0, then your space is ADS3. I mean, it's not the whatever.
What is this insertion operator?
Oh, well, sorry. Yeah. So this insertion operator. So let me just like this. I take T to be a 2 form with values in the tangent bundle. And then this contracts the 3 form in this way.
It's a derivation.
It's a derivation when this is just a vector, right? You can define. You have a form and a vector, then that's a derivation. This one is more complicated, not good. But it's linear. It's very nice. Very nice. So we found this neat way of writing a structural equation very useful for the forming. So you can deform torsion classes all at the same time, right? So now let me rephrase all this that you have heard a few times in a different way. So let's ask: is there a differential? I'm going to call it D check that squares to 0, which encodes this geometry. That is there an analog for the manifold G2 structure of the Dolbeau differential that squares to 0 for a complex manifold, right? The fact that it squares to 0, it signals integrability of the complex structure, right? So this is one justification for the notion of integrability here. But again, it's not such a nice, it is a confusing. So the answer is yes, and this was done in the 90s by Reyes Carrion and Fernandez and Ugarte, and they discovered what is called the canonical G2 cohomology. So consider a differential operator, D check, which is defined in this way, right? So you take a 0 form, and its derivative, its exterior derivative is the same as the Durand operator. I take a 1 form and take the D1, the D check operator is the Durand operator composed with a projection operator into the 7-dimensional representation, because now this is a 2 form, right, that decomposes into a 7 and a 14, right? So now take a 2 form and the D check operator. You take again the Durand operator, and then you project into the singlet, right? So this would be a 3 form, so you project here, and then you get 0 after that. So in other words, you have this structure, right? It is here, and what they have shown is that this is a differential complex in this way, right? So this operator squares to 0 if and only if tau 2 is 0. So this operator encodes the integrability condition of the G2 structure. Okay, so this gives rise to a canonical cohomology, as they described, on a manifold with an integral G2 structure in this sense. Right. Okay, is that?
Not such result exists, I guess.
Sorry?
Sorry. Not such result exists, I guess, for a spin 7 manifold.
It does.
It does.
It is shorter, yes.
Even
Very
shorter.
nice. I mean,
By the same people?
Yes. Yeah. It does. Yeah. Okay, so I have rephrased the condition of integrability for this G2 manifold in terms of an operator that's squares to 0, this T-check operator. So now I'm going to leave this idea to the bundle. Right? So supersymmetry imposes conditions on the curvature of the Young's connection, right? Is this one, which is then you have seen before. So the connection A of the bundle is an instant. You know, this means this also is equivalent to saying that F is a two form with values in the endomorphisms of B, but that it is in the 14 representation, right? So one can construct an operator, a D-check A, a covariant operator now, right? Which acts on forms with values, say, on the endomorphisms of B, which are the ones who will be relevant for us in this way, in the usual way that you find covariant derivatives. And then you do the same as you did before. Now you put an A here, everywhere, A, all over, yeah, the same projections. And then what you have is that this operator squares to 0 if and only if your manifold has an integral Lorentz structure and you have an instanton. So this is a nice way to package the idea of an instanton and integrability of the Lorentz structure.
Are these finite dimensional? These?
No. No. So I will say, I will advance this now. The Bianchi identity is what makes cohomologies finite. This, as they are, they won't give you any moduli spaces. So,
these are elliptical.
yes, they're elliptical. We proved
Right.
that.
Yeah. The cohomologies are finite manifolds.
Sorry?
On compact manifolds.
On compact manifolds, yes. Sorry. Actually, let me discuss this when we see this later. Yes. So this leads to some cohomology groups of this sort, right? So I was answering a different question. Yeah, very good. So let's talk about the finiteness of these things, right? So now we have the anomaly, right? On top of everything, we have this anomaly cancellation condition, right? That is given by this equation, right? So you have H, your flux equals the torsion. In this case, is the torsion of the G2. But now, so up to here, we have had supersymmetric, I discussed the supersymmetry conditions. But what has been proven is that a solution of the supersymmetry conditions, which also satisfies the anomaly cancellation, automatically satisfies the equations of motion if and only if the connection theta here is an instant. So it must be an instanton, so we also can also construct these check cohomologies for this connection. Okay, so this is a summary, what I just said. So the summary of this, but now I have rephrased. So this is what we had before, right? So I have, oops, what is it? I have rephrased this condition of integrability an instanton in terms of these check cohomologies. All I added was the Bianchi identity, as you have seen it in the previous slides, which is just the exterior derivative of this result. So the question there, right, is that before discussing anything else, right, are there any examples? Before discussing more, I just rephrase, I'm just trying to rephrase what the heterotic system, but are there any examples, right? So we have seen some examples, right, in this conference, and Magdalena talked about one of these here, and so on. Okay, so something went wrong here. I'm sorry. This is jump.
Skip forward.
Also, I think I'm jumping.
You're going the other way.
I'm going the other way around.
Yeah.
Sorry, this is because I should hold it with my right hand. Thank you. Yes, that's what I was constrained. So we have a summary example. So this is just a reminder of the ideas. How I haven't told you what this operator is, right? Not yet. I haven't told you what this is, but you see where I'm going, right? So the idea is that now using the Bianchi identity will allow me to describe an operator that equals to 0 and that encodes the G2 system, right? As follows. So now I will just give you the answer, right? Instead of how we found it, which is a nice story, but for this talk, I'll just give you the answer. So consider this operator, right? So we have a number of connections that you've already seen. In this operator, you have this differential here, this covariant derivative for the bundle and for the tangent bundle. We have a new connection here, d zeta, right? Find here, which this will be acting, of course, on forms with values in the tangent bundle. And d zeta is a connection with the wrong sign of the torsion, right? It's what people call the Hall connection. So this is d zeta is. And then you already saw what the A is before, right? And there's a similar one for the theta. And I only have to tell you what the diagonal terms are. So I just rewrote the differential here, so I don't have to click back, right? So what are these F and R? So F is a linear map that is defined, that acts on K forms with values in the tangent bundle and values with the homomorphism like this. I put it in a vector like this to illustrate what it means. So Y belongs here and alpha belongs there, right? So this map acting on Y is just again an insertion operator. In this case, Y here, right, is a form with values in the tangent bundle. So it's to be explicit, we have Y by F, which is again, this is a one form with values in the tangent bundle, and then we contract with one form. And then acting on alpha, right, which is a K form. So I said one form, actually, this is a K form. Sorry, later on we're going to talk about one forms there, but this is more general, can be defined in K forms. This here. Right, so alpha is a K form with values in the endomorphism of alpha. So then you have to take a trace to get something that is a K plus one form with values in the tangent bundle. And there is something similar for R, where you have to replace B for the tangent bundle instead, right? And F for the curvature of theta. So it's not a trivial. So it's not a trivial object, and it took us a while to figure this out. But so then the theorem that we proved is that if you have a manifold with a G2 structure phi, a bundle on Y with connection A tangent bundle of Y with connection theta, and we let zeta be this connection, one form on the tangent bundle defined earlier, right, with the wrong sign of torsion. Then we consider the derivative that I had defined before, and then you can prove. So the theorem says that this squares to 0 if and only this is a heterotic system. Right. And where the check here is the same projections, is involved the same projections as we had before. Right. So
So can I ask, in this G2 case, so you obtain the full system, it's not because in the 6-dimensional case you only obtain like the holomorphicity condition from this.
yes, exactly. So in the SU3 case, you only get the holomorphic side, and then you have to argue about the other part, right? When I said that you can derive everything from this one, then you get this doesn't need anything else. But yeah, this gives you the full thing. Right, so let me just comment on the proof. I mean, the proof is not trivial but straightforward. You just do it, right? And it's not too hard to see that the squaring of 0 this thing gives you the heterotic system, right? Is satisfied for the heterotic system, as long as the Bianchi identity of the anomaly is satisfied. The converse is more involved, and in particular, the vanishing of the 1-1 entry here implies the Bianchi identity.
but can I say something about the converse?
Yes,
So
yes,
we
do.
actually need to argue physically there.
Sorry?
This is where the order by order alpha prime.
Yes, go ahead, say this,
Yeah,
because
well,
it's
the
interesting.
converse is only true when you take for alpha prime small and also probably needs a lot more analysis to make
Yes.
rigorous mathematical analysis.
Yes, thank you. Okay. Okay, so now we have seen this equivalence. I mean, I really don't want to say more about this because it's, as I just said, it's straightforward, and but you need to do the computation again. Okay, so now what I want to do is to move into a discussion of what we mean by the infinitesimal moduli, right? What we're going to do. So let's start with a manifold that has an integral G2 structure and consider small deformations of this object, right? And we set phi at t equals to 0, this would be phi. So the idea, and this idea came from Karigiannis, right? That is to study the interval. In fact, his idea doesn't involve integrability at all. I mean, it's for general G2 structures, where he studied flows of G2 structures. And what he did is that he studied this in terms of a one form with values in the tangent bundle, right? So that a general variation of the free form has this form. So this is again an insertion operator in this way as before. And you can prove that if you say this, you can prove that the first order variations of the metric are given by the symmetric part of M here, right? And the determinant is given by that. And then you compute the dual of your deform G2 structure, and you obtain that infinitesimally, the fourth form varies in this way with the same M as this is only infinitesimal. So our question here is that M is like a matrix, right? It has 49 entries, whereas these two have 35 degrees of freedom. And what happens is that these contractions kill the 14 part of the 14 part of the antisymmetric part of M. So M contributes here with the symmetric part, which varies, changes the metric, right? And gives you, this decomposes into a singlet, a 7 and a 27. So the singlet is associated to the trace, and the 27 part is associated to the traceless part of M, traceless symmetric part of M, and they are both associated to this. And then there is a 7, a symmetric part of M. The 14 drops out, and the 7 stays there, but that leaves the metric invariant. It can still vary, but it leaves the metric invariant.
You can do this because it's integrable, right? Otherwise, you will need to consider more general.
No, yeah, this was posed by Karigiannis in general. He wasn't thinking about the integrable G2 structure at the time. He was just considering flows of G2 structures and describing them in terms of these.
My point is, if you vary, the more general variation will be by a free form, right? And here you're only varying by.
This is a general variation of a free form, right? It gives you a general variation of the G2 structure, right? It gives you a general free form, and then what the question that we want to ask is what variations leave the structure integral, right? That's the question we want to ask. So we computed this by using the structural equations, right? You want to preserve the fact that tau 2 is 0 as you the form, and then you find an equation that looks like this, right? So this is the D-check operator on Z, on the zeta connection, right? And then there's an insertion operator. And this looks strange, but it's exactly the same as Karigiannis would have had if he had set tau 2 equals to 0. In fact, when he computed the flow of he computed the flow of the torsion classes, right? So this it boils down to this. So we just rephrased it basically. Of course, these are deformations preserving the integrability of the G2 structure, satisfy this equation, and then you have to mod out, if you like, those that correspond to diffeomorphisms. those that correspond to diffeomorphisms, right? So you consider the derivative of psi, for example, and you find along a vector in tangent bond. And what you see is that those m's that are D-check exact in this sense, right, are those that correspond to the diffeomorphisms. So you can conceivably construct some space of infinitesimal deformations and integral due to structure, but this is the one I meant for. This is in general not a finite space, right? This is to lose in some sense. The exception, of course, is if you take the if your manifold has to holonomy, and in that case, right, you recover the work by Joyce, right, which this corresponds to the RAM cohomology. So now let's try to do small deformations of the bundle. Let's add the bundle now. So what do we want? We want to form the formations of the integral structure of Y, which preserve integrability as we did before. But we also want to deform the formations alpha of the connection, right? So of the instanton connection, such that simultaneous deformations of the G2 structure and the connection preserve the instanton condition of D. Right. So this is a question that I was asked in the late 50s by Atiyah for holomorphic bundles, right? Formation of holomorphic bundles. But this is now for this case. So again, you vary this. I mean, these two computations are again straightforward. You just do the variation, right? You vary these, and you find this equation. Then you find that the D-check A of alpha, right, is this map that we had before. So this is just as a reminder, it's just an insertion of parameter with M, right? And the check means that you have to project, right? So what this is saying is that F maps M into a 2 form with values in the endomorphism of B, which is exact in the A cohomology. So this is what we have so far, the formations of the bundle manifold, right? So we have these two equations. And you can say, well, okay, I will call these infinitesimal deformations. I'm going to give it this name. And they are given by this expression here, where the kernel of F is of course contained in the deformations of the G2 structure, and picks out those deformations that preserve the instanton condition. And again, there is no reason why this should be finite at all, finite dimensional. Right. So now we need to add the last bit, right? We need to remember that we have the anomaly cancellation condition, so we need to do variations of that, infinitesimal variations of this. And so what we found is the following. So if I call Z a one form with values in this bundle, then I take my operator and apply it on Z, right? Like this. So kappa here are the formations of the tangent bundle, right? And so this is what you have from the operator we had before. And what we have is that the equations for moduli satisfy this here. The D-check of Z is 0. Right, so we already have seen this one, right? In the previous slide, we saw this one. So this one. This equation here, right? And then, of course, we have this one that doesn't look like the one I showed before. Right, so this one in particular, the first term, the first entry there, turns out to be the equation as this one, right? The formations that preserve the G2 structure, integral G2 structure, but you have to use the anomaly cancellation condition, right? And moreover, It is true only if you identify the degrees of freedom corresponding to the antisymmetric part of Y, right? So Y now is a one form with values in the tangent bundle with the covariant variations of the B field, right? So what's being said is that Y is a one form, values in the tangent bundle, right? And I can separate, and Y, I can split it into a, so I didn't even do it with two. I can write it as a matrix if you like, using the metric. And this will have, and we call it M to connect what we had before. You have a symmetric part, and then you have an anti-symmetric part. Right, so this will correspond to the formations of the metric. And this here, you need to identify with this B. Right, so we had before just a 7-part in it, and now we have also this actually has, this is a 2 form, but you can think now this is a 2 form that has a 7 and a 14 part. Right, so now you identify the 7 and the 14 part with the variations of the B field.
Why is this so? Does this follow from any of the equations that you have?
It comes out like that. I mean, this is not something we put out of our hat. I mean, it comes out like that.
So you need it.
Yes, I mean, if you look at the previous equation here, so we have this operator that squares to 0, right? And we constructed so that gives you the heterotic system, and so acting on BZ gives you this, right? So if you want to identify this, so then on the other hand, you vary your H and your Bianchi identity and everything, and then you compare that with this, right? And when you compare, you find that you get that these are the modular equations as long as you do that identification. It just comes out like that. Right? So it doesn't. I'm not sure what else I can say that would be more illuminating. But it's in this step. And so this is in all this story, one had to vary H, right? Not just the bundle and the metric. And this is the variation of H. So this second term comes from the variation of the Chern-Simons terms. And as you can see, this is a covariant of this invariant to the gauge transformations, right? So this must be invariant. So whereas the B field wasn't a well-defined object before, the derivative of the variations is a well-defined treatment. Right? So it behaves better than the B field itself, right? So you have to, so someone here in this audience needs to tell me what kind of Jervy object this is, right?
And is it compatible with this equation? So the fact that you identify the antisymmetric part of YT with the variation of the B field,
yes,
is it compatible with this? Yes,
it's all compatible with this, precisely, yes. Yeah, no, this is a large chunk of the paper is precisely in doing this. Right? I don't know. Can you say anything that will illuminate it? No? Apart from doing the computation yourself, I don't see.
As you said, if you want to identify the modular equation as d check of something equals 0, then that's
yes, yeah. So you are constructing. You are the whole exercise is to construct an object that when the potency gives you the equations, the heterotic system, and then the first cohomology gives you the modular, right? And then you have that. Right, so then this Y here, right, contains not just the formations of the G2 structure, right, contains the formations of the B field, and then so it mixes up the formations of the G2 structure, the metric, with the formations of the B field, which is what you would have expected anyway, right? So if you try to look at sigma model perspective, for example, this is what you would have expected. So then that's your space of the small deformations, right? This is given by this object, and you can show that object that can be exact correspond to diffeomorphisms, case transformations, and I forgot to say that there is also an ambiguity here because the object that is well defined is the derivative of B, right? So this is up to, so this includes a kind of symmetry in this case, in which you can change this by a closed form, an invariant closed form. So, and in this case, actually, we check that it is the Bianchi identity that makes the whole thing finite dimensional. And I was saying someone with breakfast or dinner the other day, right, that if you have just the bundle from manifold, and you have asked, what do I need for my the tangent space of the moduli space to be finite dimensional, you almost end up with a Bianchi identity. So it is crucial. I mean, this makes the system very rigid, in fact. Yeah. So this is the main result, right? So we have a heterotic structure, right? Then there is some special structure on these bundles Q, right? That's an important particular equivalent to some operator that is nilpotent, and that you can identify small deformations with the first cohomology of this object. So of course that's all I want to say today. I mean, I could go on and on and on, but I think that's not one. So let me just give an outlook and open problems. So as I said, we want more examples. We need more examples to play with, right? And who can compute these cohomologies? I mean, are they practical? I mean, can we say anything about them? Why I regard what I just told you just a first little step. I mean, discussing small deformations of the system is something that we were, as hard as it was, I mean, it's really a small deformation, a small step in the full deformation problem of theory. So what is the mathematical structure of the heterotic system, right? So of the moduli space in particular. So this is very important in the physics, right? To understand the physics of it. But then there are all the global questions. I mean, Philip told you, for example, of the metric for the Schrödinger system. So what can we say in this case? What are the singularities, higher order deformations and obstructions, everything that you want to know in deformation theory, to the proper deformation theory. So in the SU3 case, we progressed a little, right? In the SU3 case, for the whole Schrödinger system, we used a superpotential to understand higher order deformations. So superpotential is an object that one obtains from physics, from your Lagrangian, right, from the dimensional reduction of your theory. And so we wrote the superpotential for the SU3 case existed for a long time, but we did this for the G2 case. So this is an object that we think will be very useful to understand higher order deformations. And we were very successful in the case for the SU3 case, and which one, if you ask for the analog of the Moret-Cartan equation, it's in that case, you end up with an L3, like an L3 algebra. So in this case, so this superpotential, the extremum of this superpotential, give you the heterotic system in particular. And notice this extra bit here. This is because this comes from the 10-dimensional theory. So this is the extra 3-dimensional, the flux in 3 dimensions, this little h. And we showed in this paper that h equals tau 0/3. So when this is, and this is also proportional, I mean, as Matteo was saying, the square of this is proportional to the curvature of the ADS3. Right? So the claim I made before that tau 0 equals to 0 gives you Minkowski space, and tau 0 non-zero gives you ADS. So So we have work in progress trying to vary this to higher orders. This is very hard, really very hard, because the parametrization is complicated to understand. But we did manage to show that the questions I showed you before for infinitesimal moduli are precisely the second order derivatives of this superpotential. Right. Then, of course, the next another way of looking at this is this from the sigma model perspective. Sigma model perspective. For heterotic case, you want to consider 1-0 superconformal, minimally supersymmetric case. You want to consider superconformal nonlinear, two-dimensional nonlinear sigma models with a target space, which admits some G2 structure and a bundle with connection. And this gives a sigma model with extra symmetries, right? These are called the Papadopoulos symmetries. This was done originally in '92 with Marc-Antoine. We generalized this to the heterotic case to include the bundles. So which gives symmetries, which give Carol currents, and so there's a whole story here coming that we are trying to pursue.
1,0 is because you are compactifying to 3 dimensions?
Yes, exactly. So you could have 2,0, for example, and you can still compactify to 3 dimensions. Okay.
Yeah, I think here 1,0 is more because it's not an heterotic thing.
It's a heterotic thing. This is the minimally supersymmetric case in the heterotic case. So this is the Papadopoulos did this for the bosonic string, right? And what we have now is added the bundle. So you need to add, apart from your bosons in your sigma model, you need to add fermions that accompany the gauge potential and so on. So it's a very nice story, and you do get the symmetries if it is a statement that you get the symmetries if and only if you have a heterotic system, right? After you cancel anomalies. It's a complicated story. So again, here in terms of this, the moduli marginal deformations of the sigma model, right? If this was done by these people in the case in which alpha prime is 0, right? So there is already a step into these computations, right? So, and finally, there's more. I mean, this is just a perturbative story that we told you there are 5 branes that you can correct the 4 form. What are what are the non-perturbative corrections to the heterotic system? What are the generalizations of Donaldson-Thomas invariants, concepts of mirror symmetry, who need the non-perturbative corrections to properly, right? So when is it the case that you have 2 physical theories, 2 heterotic systems that give you the same physical theory? That's what I would call a duality, right? So this generalized mirror symmetry was a very nice talk on this work in 2-0 mirror symmetry already. And of course, might be useful to relate this to other theories. I mean, there are dualities with other theories, right? So there is this, the reason I put all this is just to make you even more tired with everything that we need to do to be able to go just a little bit step by step into this story, right? Okay. So I think, well, thank you very much.
Yeah, I think at some point you said that at least in the case of G2 holonomy, your complex is elliptic.
Why did I say that? For the G2 holonomy case, just for the deformation of the manifold, this boils down to the one per choice.
These complexes are all elliptic. You don't need to.
Then
oh yes,
I'm confused about the non-finiteness of the
Sorry?
cosmology. Then I'm confused about the non-finiteness of the cosmology.
If you don't care about preserving the anomaly constraint when you deform, then you don't have any, and there's nothing that says it's finite dimension.
This is like the conformally balanced condition, right? In this is analogous. If you take this statement is analogous to what you were saying in the SU3 case. If you just take the manifold with a conformally balanced condition, you can show that if you do small deformations of that, the space is infinite dimensional. It's the same kind of statement. Yeah.
Yeah, so I was wondering if then you can carry this program of having a harmonic representative on the cohomology classes, and it is determine special deformation directions that mean anything physical.
Eric is laughing.
Well, that's probably somewhat related to figuring out what the correct locator potential is.
Mhm. Yeah, so yes, at this stage we don't know, right?
There is no Taylor potential in this case.
No.
There is a real.
Ah,
Yeah.
but it's not a Taylor potential.
Yeah, this formula should be, you have this formula for the supergravity potential. And I think it has the same kind of form in terms of a real get potential and not real.
Okay, but you just are for analogy, you are calling it Taylor potential.
Yeah, sorry.
Okay.
Yeah, no, I think, I wouldn't call it, yeah. So there is no carry potential for a metric, right?
There is some sort of potential. It's
But
just
yeah, that's what we want to figure
not-
out.
yeah,
But it's like a Hessian manifold, then?
Sorry?
It's like a Hessian
I
manifold.
think so.
Yes.
Yeah.
Yes, that's what we expect. Some Hessian, yeah.
In the complex that you have describing these deformations, like which degrees are present there? You have 0, which are the symmetries. You have a -1 as well.
No, we have the 0 forms in this complex who correspond to the symmetries, including the form of.
But no -1. But you mentioned at some point the B field, like that you could actually change the B by.
Yes, so there is a symmetry that it changed. Yes, because this B field here, right? So let's go back to right, that one, right? So when you vary H, right, as I said, this is the derivative of these variations, right? It's a well-defined free form, right? So this is what you obtain, and then the 0 forms carry some symmetry that if you change the B field by some close,
Yeah.
then that doesn't change anything.
Okay, so
That
like
doesn't change your modular.
so this kind of change by a B field, is that also present? Like the fact that you can put 2 forms and not change anything in your system, like is that included in the complex, or it's something?
It is included in this. Yes.
It's included in the Y.
Yes.
Y, kappa, and alpha. Those are all of the deformations. They're all in the same degree, right?
Yeah, they're all 1 forms in this case, right? So
But like the Y is appearing. Okay.
So the Y's are 1 forms in the tangent bundle. The alpha is a 1 form in the double.
So I'm thinking to be like, should I think of this ability to move things by closed forms or exact forms as some sort of Hamiltonian symmetry, or?
I don't know. Maybe. I don't know at this moment. I mean, standing on one leg, as I say, how to translate this.
Okay. But like I can always add a closed thing and then nothing changes, right?
Yeah, for this piece.
In the 2 form part.
Nothing should change, right?
Nothing changes.
Between diameters and that.
Okay. And the complex, how it starts at 0, 1, 2, like where does it stop again? Like I forgot.
It's 3.
3.
Yes, the complex at the very beginning, right?
Yeah.
Oh, there, yeah. So there.
Right. So your structures are in 1, right?
That the moduli are 1 forms, yes.
Right.
And so you have derivatives starting on 1 form. So it's this point here.
In this complex, if I apply d 3 times, but I don't have tau 2 equal to 0, like, but I can just, because you can always write this complex regardless of whether they're integrable or not. Right?
Ah, yes, you can, yes, but then you wouldn't have the nilpotency, right?
If you apply 3 times.
If you have an extra.
Go from 0 all the way to 3, 1. What happens, do you know?
No.
Okay.
No. So what happens if let me see if I understood your question. What happens if
In the non-integrable case, he's asking if you start at 0 and apply d.
Yeah.
D.
Then he wants to know if that potentially is non-zero.
Yeah, I'm just thinking like when you have curvature, because like the curvature equals to 0 is this square equals to 0, but the d of the curvature is always 0 no matter what. So I'm just wondering if there's that kind of also Although also
Bianchi
for that Bianchi
identity.
identity,
Yeah.
but completely different from what you're talking
So your problem is, as you are suspecting, the problem comes here with integrability, right? So only when you have the integrability condition, you can have a singlet there.
Sorry,
In fact,
only when
when you have integrability condition, you can have a singlet here. These projects are free form into a singlet part. So a general free form has a singlet of 747.
but like this decomposition is just because you have a G2 structure, right? It has
Exactly, have an integral. So, but what I'm saying is that the main problem when you don't have integrability comes here. But you can project into a singlet if you
because like this last part, it doesn't seem to be very related to your problem because like this one is where the structures are,
Yes.
the two is where the integrability is. So
Yes.
like in principle, if you had stopped at two, you'll already be able to get your all your theories, just that it's extra piece at the end.
The study of obstructions, perhaps.
Maybe.
That's right. That's right.
Exactly.
Yeah,
When one studies obstruction, then we will have to see. We have this for the SU3 case. We have this story with this algebra, but have we answered the question about obstructions there?
Well, we have the more economic equation.
We have the more economic equation.
So the obstruction should
Yeah.
live in H2, so this
Yeah.
obstruction should probably be related to.
Exactly.
H2 there as well.
So our own wild speculation is that we will have something like that here, like perhaps an algebra if we're lucky. Yes, if we're lucky, and then we will be able to talk about obstructions.
There are sort of physical speculations that makes us think that there should be an L4 algebra.
For algebra, yes.
Does
But for
this
this, sorry.
Does it have Poincare duality, this complex?
You mean like H1 equal H2? Yes.
That's it.
Well, no, the Q. The Q value. So yeah, H1 of exactly.
H1 is equal to H2.
Well, if on a G2 Hamming manifold, these are all zero actually. All the
Well,
combinations.
the G2 homology 2 is different from 0, right? So the 0 is 0 and 2 is G2.
2 and the 7, there are no harmonic 7. Basically, these are just the harmonic 2 forms and 3 forms in the appropriate representations.
Oh, the representation, right?
Yeah.
Yes, sorry, this apologies, yes. So the subindex here is so 2 forms decompose into 7 and a 14.
7.
So these projects,
Right.
so the D acting on a 1 form, this is your 2 form, and then the check is the projection into the 7 part of that.
Right, I forgot that, yeah.
Yes. And then here, when you do it again, you project into the singlet, and that you cannot do if you don't have integrability.
Any other comments?
Comments.
Question is
So if I understand correctly, in the type 2 case, one can phrase these conditions on supersymmetry in terms of some generalized complex structure in this exception.
Yes, exactly. Yes, this is what. Yeah.
And is there something similar in this case? Like you will have some like direct
There must
structure.
be. Yeah, I agree that there must be some way of translating that into this, and
Do you know
people
what?
must have tried this. I haven't, but and I don't know. Do you know? Somebody has tried this to write down, go back to the type 2 theories, and whether they have tried to write down these statements on generalized geometry for type 2 theory, in terms of something like this.
Like for example, encoding this condition in supersymmetry as the extent of some generalized direct structure.
Right.
Yes,
Or are
yeah.
you talking about the heterotic or type 2?
Sorry.
He's asking about type 2, right?
So this is not in type 2. I'm just asking if something similar can be done here. If you have some like exceptional.
Oh,
type
the
of
other way
value in a
around.
sense,
I see. Well,
I wrote a paper with Carl Tipler and Andrew Clark. We have that in
Okay.
section.
which one is your paper?
It's the one with Andrew and Tipler.
Yes.
With Andrew Clark, and
Yes,
we do
yes.
the general geometric description.
Yes.
But in the type 2 case, there is the Mandat-Nunez-Novo theorem, so all these fluxes will be 0 on a compact manifold.
In the type 2, it's very different, right? The type 2 theory, you have a manifold, but you don't have a bundle. What you have is a set of forms and some other equations that.
I know,
yeah.
that's what I'm saying,
Yeah.
that unless you do something else, like including high order correction of sources, So the moduli problem trivializes in the sense that on a compact manifold, all the fluxes are going to be zero.
Okay.
So a priori, the same problem, the analogy is not so clear.
No, I could see. I agree with you. Yeah.
That I don't know, but that would be, for example, I've never seen something like that problem. So. In those cases, in many of those cases, they inform the audience that this is a local analysis, and if you do it in a compact manifold, you have to include ingredients, as you say. I don't think so. Maybe they have done it by now, but I'm not aware.
All right, we have 3 entities to thank, at least.
Yes.
The first is Xenia for her beautiful talk. So all of the speakers who did, in my opinion, an unbelievably good job.
Yeah.
Third is to the organizers who make this conference possible, and to whom I have only one criticism, which is that we did not get a chance to hear from them. They should be the ones speaking. Maybe we should do that on Saturday. But thank you to Mario Garcia Fernandez, to Roberto Rubio, and to Carlos Shapazi, who did an excellent job in organizing this event.
Oh,